Good afternoon, everybody. Thank you for those that have joined us. Over the next hour, we are going to talk about additive manufacturing testing, from prototype to performance, mechanical testing, and fatigue qualification in additive manufacturing. So just to introduce myself and my co-host. So joining you today is the two of us. My name is Mark Overson. I'm the Product and Marketing Manager for Dynamic Systems here at Instron. And alongside me, we have our subject matter expert, Rebecca Rife Musgrove. She's our Electropulse Business Development Manager. So just before we go into the presentation itself, just a couple of bits of housekeeping. So just to let you know, we will be recording this webinar, so you can focus on the webinar itself without need to scribble down notes or anything like that. As well, within the webinar, we're planning a question and answer session at the end. So type any questions you may have into the chat box or anywhere, and we'll pick them up and we'll look to answer them at the end. We should have a decent amount of time to answer questions, so don't be shy. Ask whatever you want to ask. And then finally, as I mentioned, it's being recorded. So what we will do is we will upload this recording to our official YouTube channel at Instron Official so that everybody can access it at a later date should they need to. Okay, without further ado, I pass over to Rebecca.
Thanks, Mark. Yes, so today I'll be talking about mechanical testing and fatigue qualification in additive manufacturing, especially considering the transition from prototype to performance. So what I want to cover today, and hopefully you'll take away by the end of this, is firstly the additive manufacturing fundamentals. So for those of you who may be less familiar with additive manufacturing, I will just briefly touch on some of the main technologies and materials. And then I will be talking about both the challenges and then implications for fatigue testing, as we have observed here at Instron, followed by a question and answer session if you do have any questions. So as Mark said, please place any other questions in the chat, or feel free to privately message them as well if you want to remain anonymous. But first, why are we discussing this now? Additive manufacturing is an industry, it's a huge market. So right now, the estimate is anywhere from around $30 billion, of course, depending on which source you might look at. So it's already huge. So you might ask, why now? Well, the growth rate is very large, again, depending on where you look, anywhere from 20 to 30% capital annual growth rate, which leads us to estimates from a 2030 market of, $90 billion. So we're seeing huge market growth at the moment, which of course is translating to more and more testing that we are seeing at Instron. But it's not just growth, it's particularly how the testing market and the additive manufacturing market is changing. We are seeing far more production parts rather than prototypes. So when additive manufacturing was first introduced, it was often, those small plastic parts being used as prototypes for then the final model that was still being used traditional manufacturing. Whereas nowadays we're seeing more and more production-ready parts rather than prototypes. So for example, I've got just a generic example data sheet from one of the additive manufacturing printer manufacturers. And you see we quote the tensile strengths, the yield strengths, elongation after fracture. These mechanical properties are becoming more and more important as we move into production-ready parts from additive manufacturing. And it's not just production, we're also seeing a shift to more structural usage, especially in long-term load-bearing fatigue. So this is where that fatigue testing comes in. It's not just one tensile test for one strength measurement. We're seeing that parts are being used long-term in real load-bearing application. So this example was a press release from Stratasys and Airbus at the end of last year, December 2025, saying that Airbus is producing more than 25,000 flight-ready 3D printed parts annually. And that's obviously completely transforming how aircraft are built and maintained across the global fleet. And this is not an isolated incident. We are seeing more and more aerospace, automotive, biomedical, you name it, industries using additive manufacturing, not just for production, but for production of safety critical or long-term load-bearing parts. So this is why we're addressing this now. We're seeing fatigue testing of additive manufactured parts more and more. So what are the technologies? So as a refresher for those of you who may be less familiar with additive manufacturing, when we say additive manufacturing, this is also commonly known as 3D printing, and it's the process of creating three-dimensional objects by building them layer by layer, often from a digital design or digital model. And this can use a wide variety of materials nowadays. So you might typically, when you think of additive manufacturing, think of material extrusion, also known as fused deposition modeling. You can see on the graph on the right that has one of the highest shares of additive manufacturing. And that might be something that's typically available to a consumer with a plastic or a polymer. But we see additive manufacturing being used for polymers, metals, ceramics, composites, biomaterials, and more. And it allows for the creation of complex geometries that's difficult or sometimes even impossible to achieve with conventional methods. And there are many other advantages to additive technology, including reduced material waste, much faster prototyping, increased flexibility, or even customized components. And so we really see this used across a wide range of technologies. And just on the right, as I said, that table, I've just got a reference from all the different technologies that you might see. So material extrusion, powder bed fusion, that photopolymerization. And you'll see that in terms of the processes, it's a real test of your acronym knowledge. So we have fused deposition modeling, laser sintering, laser melting, electron beam melting, and more. I'm just going to focus on three technologies, the ones that we might see the most often, certainly as Instron, especially for the structural parts. So the first one, as I said, fused deposition modeling. I wanted to touch on this because this is really, when we say 3D printing, often this is what people think of. It's the most widely recognized additive manufacturing process. That works by melting and extruding a filament through a nozzle, typically, as I said, using thermoplastics. But while it was historically limited to polymers, we also now can see it for metals and fiber reinforced composites. So recently I saw people were printing metal powder in a polymer binder, and then they burn off the polymer binder to create that metal part. In terms of microstructure, we do end up seeing clear lines from the extruded metal within the structure, which are obvious structural weak points potentially. And yeah, as I said, these printers are the most widely commercially available, and even many individuals have their own FDM printer as well. Moving on to something we see a lot more for structural parts is powder bed fusion. So these technologies use any heat source to fuse powdered material, typically metal, but also polymer, layer by layer. So we have, and as I said, this is a real test of your acronyms if you're in the additive manufacturing world, with SLM, so selective laser melting for high density parts, selective laser sintering for polymer parts often, electron beam melting that can be used for reactive materials, things like titanium, and then direct metal laser sintering as well for precision parts. And where we see this typically, as I said, we do see it for structural components, and it's most frequently used for small to medium complex parts. And then the final one I'll touch on, because we do see it as well, is directed energy deposition, or DED. And this is a process where melt the material using a focused energy source as it's deposited. The most easy one to wrap your head around is often wire arc additive manufacturing. You can think of it as effectively a controlled welding process. So if you use that weld to keep building and building up a 3D part. And this is a really high deposition rate variant, so it's very suited for producing larger metal components, as it's often more cost effective than the powder bed fusion methods for the large scale builds. So those are the three that I see the most often. And so with these different methods of creating a part, we see different challenges as they come to fatigue testing. So throughout this talk, I'll touch on 4 of these. I'll touch on the effect of defects, variability, anisotropy, as well as size. And don't worry, I'll define all of those as I get to them. And I'll talk about their general implications for fatigue testing. And firstly, what I want to clarify is that in many ways, there are none. A fatigue test is still a fatigue test. It's still defined by a stress ratio, you might see on the y-axis on the right-hand side, and a number of cycles to failure, which you'll see on the x-axis on the graph. And you see that we still can build up an SN curve based on fatigue for additively manufactured parts. So it's the same in that respect in terms of definition. However, beneath the surface, or often on the surface, the differences in microstructure and production method can really dramatically change the properties. And what we've seen is experimental evidence generally showing that the fatigue strength of additive manufactured parts is lower than those of their equivalent conventionally manufactured parts. It's not always the case, but it is the general case. So I'll go into what maybe causes this and each of the different challenges. So first was defects. So what do I mean when I say defects and why is it happening? Well, additively manufactured parts are composed of thousands of small incremental casts that build up to make the final material rather than one bulk cast. And so we can get defects at where these casts join, that include things like porosity, a lack of fusion between the casts, and also very high surface roughness from these individual melt pools. And post-processing can reduce these, so things like machining, heat treatment, but we don't always eliminate these issues. So what is the effect of these defects? Well, as you may remember from any material science class you may have taken, defects act as stress concentrators. So when you have a concentration of stress in one area, it can promote early crack initiation and therefore a lower fatigue life. Additionally, when we have high surface roughness, which we get in the as-built condition for additively manufactured parts, we also get surface crack initiation sites, which again further reduces the fatigue life if you start a surface crack that can run through the part. Beyond this, we're not helped, and the lower fatigue life is further exacerbated by high residual stresses from the thermal cycling and the high thermal stresses during the additive manufacturing process that, when they want to be relieved, also cause early fatigue and early cracking. So that doesn't all sound great. So what do we have to actually consider when we're looking at defects? Well, the first, as I mentioned, post-processing can play a really critical role in improving that fatigue performance. So people are often will consider surface machining, and so this is often defined in perhaps the standards you might be using for testing. They will define a particular surface roughness, or indeed chemical etching for reduced surface roughening, and also heat treatments. It's very common to see people using heat treatments on additively manufactured parts to reduce those residual stresses or perhaps blunt the internal defects and improve fatigue performance. And because of how critical a role these play, it's really essential to document and define the post-processing during testing. So there are different ways defined in standards by, for example, the STM community. But one simple way of doing this is just making sure it's written down with your test results. If your test results are completely dependent on the conditions. This is why we introduced specimen and task details into the Instron Wave Matrix 3 software, so people can write down in the properties their heat treatment, their surface treatment, any other treatments that might be critical to the testing results. So that was defects. And now I'll move on to variability. So the challenge with additively manufactured materials is we often see increased variability when we compare them to their traditional parts, in part due to those defects we just mentioned and how it's not always certain exactly where and when you'll see those defects. So we get variability within a part, and so this is known in the materials world as inhomogeneity, and that can be due to differences in heat dissipation along the print path. So if you imagine a very thick area of the material, it will take longer for that heat to dissipate compared to a very thin part of the same print. And you get differences in heat dissipation, you get differences in material properties within the part. But it doesn't stop there. We also get variability part to part, maybe due to the different parameters or print path, operator to operator, machine to machine in terms of the additive printer, and also with different process or production parameters, we get variability. So as you can see, there are a lot of different sources of variability, both within and across parts. And well, what is the effect of that? It might seem obvious. Higher variability leads to higher scatter in results. With fatigue testing, where they're even more sensitive to very small changes in defect density, etc., compared to tensile testing, you might get even more variation, as fatigue testing is so sensitive. And what this means is we also can't use that as an excuse. So if we see fatigue results that are very scattered from additively manufacturing, we also have to correctly identify whether that scatter is from that true material property variation or from other factors. So I just put a quick example here. I had a colleague do some testing internally, and they saw very high variation in their scatter in their results. And it actually turned out that it wasn't the material itself changing, it was the increased surface roughness that led to slight changes in cross-sectional area that kind of introduced false scattering to the results, as the incorrect stress was being calculated by using a blanket cross-sectional area across all of those. And that colleague will be discussing that more in some future blogs as well, so be on the lookout for those. So what do we consider when we talk about variability? One of the first things people consider is the batch size. So considering whether the batch size is appropriate to have confidence. So if you're getting a very high scatter SN curve, often people might need more results or more confidence in their results to trust that SN curve. And we also need to make sure we don't introduce further variability. So that might be that introduced from changing printers or processing parameters. We need to make sure we minimize that variability. But this also includes the test setup. So ensuring that you use a sort of high stiffness machine, repeatable gripping, things like pneumatic grips, trusted sensors, so that when we get scatter in the data, we know that it's from the material itself and not from the machine or the test setup. Then moving on to anisotropy. So here I've combined the challenge and the effect. They're essentially the same thing. Basically, additively manufactured components often display highly directional properties, and this is what's known as anisotropy. There's a difference in properties in direction. And this is because parts are built layer by layer. So you have mechanical properties in the XY plane are typically different to those in the build direction. And we actually see generally the build of the Z direction is weaker due to those weak points created between layers. So the effect of that, and I just included it on the same slide here, is that fatigue performance does depend strongly on build orientation and the loading direction here. So what we need to consider is Because fatigue testing is sensitive to loading direction, we need to pay careful attention to both the specimen orientation, so where it's been taken from the build direction, and again, things like the specimen inputs to make sure we're writing down where we're testing from, but also the machine alignment to make sure we get consistent results. So at Instron, we have something called the Align Pro that helps control both the concentricity and angularity in the load string. Again, making sure that any change in alignment is from the material itself and not the test machine. Additionally, people often will consider axial torsional tests to investigate the effects of the differences in load properties in directional properties. So things like the shear properties we can look at if we do axial torsional tests. And again, this is something that we often see, and we often supply biaxial machines with tension and torsion to investigate these properties. And finally, we move on to size. So with additive manufacturing, not all good things come for free, unfortunately, and there is a very high cost and build time associated with printing these large volume additively manufactured parts. Additionally, we also often see parts that are pretty small. We're seeing a real reduction in the scale of the final parts that we're using as the printing technology itself improves. I've gone to fairs where I'm seeing small additively manufactured parts that are really accurate to the micrometer. And then beyond that, when we consider size, we consider the size of a sample. So what we know is that differences in print path, geometry, and the local thermal history, which are caused by often different sizes. As I mentioned, something large dissipates heat more slowly than something small. We often find that standard dog bone specimens might actually not represent the final component in terms of its thermal history and mechanical properties. So the effect of this, if you haven't guessed already, is that fatigue specimens and mechanical specimens in general are frequently sub-sized when we look at additively manufactured specimens. These can often conflict with recommended standard-driven geometries. It's often difficult to print enough material for that. Beyond that, we also see many fatigue test programs actually incorporate full-scale or perhaps representative components in their testing. So rather than a sample that looks like a standard dog bone, you get a sample that can look like anything, a part of an aircraft, a part in a human body. An additional effect with this size is we're also seeing a desire for smaller batch sizes with the rise of custom prints or even N=1 prints. You know, why would anyone want to test 30 specimens when they're actually only making one instance of that print, perhaps a super custom part that has been designed, for example, for biomedical? So the considerations that often leads us to with the size, often for gripping. So we have considerations around gripping small scale or component level specimens. So that's why, for example, in the electropulse, we have a T-slot table so people can have the flexibility to mount any custom components they want to test unique samples. It's often worth considering whether the standard that you're testing to has a sub-sized, or often it's called a miniature annex, to make sure that we're still meeting the standards. Another consideration, which has really been on my mind lately, is this general desire for more efficient data generation, but with less and less material as we go on. So I've had a lot of open conversations with people around the potential of where AI can help with this, with data analysis or correlation of SN curves, things like can we correlate printing parameters and material properties. This is something that I'm getting very interested in at the moment, and if you have thoughts on this, I'd love to reach out, connect on LinkedIn. As we said, with the rise of N=1 and custom prints, we really need to consider the role that material testing has and how we can best assist with these challenges. So that was everything I was going to cover. So I covered the effect and consideration with defects and how they can lead to a reduced fatigue life and how we need to document the post-processing really reliably. We talked about the variability that we see in additively manufactured parts, but how we can't use this as an excuse, and we need to always make sure that the variability is coming from the part, not from the machine setup or the test setup itself. Then we discussed the anisotropy and how that alignment is critical, and how maybe we also might want to investigate the multi-axial properties. And then finally the size, and how that increased desire for smaller and smaller parts or full-scale component testing is challenging us with materials testing and how it's set up. So I couldn't cover this all without also talking about the Instron solutions. So there's 4 things that I wanted to cover here. So firstly, being the electropulse, I mentioned that before. It's an all-electric testing solution that has that high stiffness needed and the high precision and really, really stable control using the patented stiffness-based tuning algorithm that we need for repeatable and reliable results that are not introducing any additional variability into our data. That can be coupled with the Align Pro, where we can get control of, as I mentioned, the concentricity and angularity, again, for that repeatable testing. Then also looking at biaxial models. So the electropulse comes in tension torsion models for the possibility of multi-axial testing, whether that to be investigating the shear properties of your part, or maybe representing real life loading conditions as well, things such as biomedical. And finally, the expertise, trusting in the 80 years of testing experience that Instron has, and the work that we've been doing with companies and industries in the additive manufacturing world, and we'll touch on that a bit towards the end of this webinar, for their guidance and support as well.
Okay, so I'll just finish off. So additive manufacturing, our clear statement here is it's now not just for prototypes, it's also for structures. And as the industry grows, we can see more and more of this this change happening. The recording, it will be posted on our @Instron official YouTube channel, so you can watch it again, should you wish, or share it with your colleagues or compatriots, either way. I will, of course, send out the presentation to everyone that's been on the call. That's not a problem. And then finally, I think we've got a bit of a follow-on with regards to our case study. We've got quite an insightful additive manufacturing video case study that we did in conjunction with TU Dortmund over in Germany, who are doing some amazing stuff with regards to biomedical applications and what they're doing. Don't want to ruin it for you, but by all means, have a watch. It really is worth having a look at that, and reaching out should you have any more questions on that side. So thank you to Rebecca. So we've got a series of webinars going on. So final slide from me and from us. So we've got another webinar, Designing for Durability, Fatigue Performance of Additive Manufacturing Components in Industry, where we'll be looking to explore the impact in aerospace, automotive and biomedical industries in particular. We hope you can join us for that one. We hope that this has been a great session for you all, and I appreciate your time, and thank you from me.
Yeah, thanks from me as well.
Okay.
Great.
Goodbye, everybody.